Okay, we're continuing with chapter 11, which is on infinite sequences and series. In this video, we're going to go through section 11.9, which is on representations of functions as power series. So again, the last part of chapter 11, the main goal is we want to learn how to represent functions as series. And in particular, we're going to do this strictly with power series. We're going to represent functions as power series. And so in the previous section, we learned what a power series was. Now in this section, we're going to get a feel for the mechanics of how to represent a function as a power series. In this section, we learn how to represent certain types of functions as sums of power series by manipulating geometric series or by differentiating or integrating such a series. You might wonder why we would ever want to express a known function as a sum of infinitely many terms. We will see later that this strategy is useful for integrating functions that don't have elementary antiderivatives, for solving differential equations, and for approximating functions by polynomials. Scientists do this to simplify the expressions they deal with. Computer scientists do this to represent functions on calculators and computers. So yeah, I've mentioned why it's desirable to be able to represent functions as series. Okay, but to get a feel for the mechanics of how we do this, it says that what we're going to do is we're going to manipulate geometric series or differentiate or integrate geometric series. So why geometric series? Well, if you think about it, up to this point, we've worked with a lot of different types of series, but there's only been two that we actually could find an explicit S sub n formula for that series, and then also take the limit of that S sub n and get a converging finite number, or at least a formula for it. That was the geometric series and certain telescoping series. Now, from the perspective of a power series, which is strictly what we're working with for the rest of this chapter, so we've got f of x is equal to the sum from the perspective of the power series. The form of a power series is very close to a geometric series. It's very close in the sense that every power series is going to have a common ratio, because this x minus a has no n. There's not a function of n in here. You pick an x and you have a constant in here. So every single power series has a common ratio. You might say, well, wait, so isn't every power series a geometric series? Technically, no. A geometric series, with a geometric series, you have a common ratio, but then with every term, like this is a constant. This isn't a function of n. So if this c sub n turns into a constant number for every n, then it's a geometric series. But if this is changing with each n, then it's technically not a geometric series. But you can see it's very close. It's very the character of a power series is very close to a geometric series. Okay, and so what we're going to do is, to get a feel for the mechanics of representing functions as power series, we're gonna start with a basic geometric series. So yes, you can represent a geometric series as a power series, and we're gonna start by looking at a is 0 and c sub n is 1. That's a basic geometric series centered at 0 with the first term equal to 1. Okay, now what's great about geometric series is that we have an explicit formula for the infinite sum of a geometric series that converges. So it's the first term over 1 minus the common ratio. So if the first term is 1 and the common ratio is x, because that's what it would be if a is 0, we have 1 over 1 minus x. Okay, now what is that equal to? Well, just make a 0, make this 1. That it's equal to that power series. Okay, now up to this point, we've typically been looking at it where we have this first, right? We are given the series first, and we and we solve for what the infinite sum is equal to, so that this is flipped. We've been looking at it this way up to this point. Typically, we've been saying, okay, we've got a series, and we do the analysis, and we solve and find that the series is equal to this. But what we're doing in this section is we're gonna flip this, like shown here. What I just erased, where we actually look from the perspective of the function first. We have this function, and we want to represent that as a power series. Okay, and what we're going to do is, starting with this, we're going to create other function representations of power series by manipulating this particular geometric series, or by differentiating or integrating it. It's going to be one of those three methods. So we're going to go through some examples of those three methods. But you can imagine, though, we're going to just strictly in this section, we're going to work with this particular, this is going to be our base, and we're going to branch off from here to get other function representations. This is going to be our base. But you can imagine that you could start with other bases, right? This was the geometric series with first term is equal to 1. Well, you could have different first terms. You could be not centered at 0, and even it's a little more difficult analysis, but you could branch off to not having the C sub n be constant for every term. Okay, but again, in this section, we're just going to focus on this simple geometric series with centered at 0, common ratio x, first term 1. So how can we create other function representations with starting from here? Okay, well, we're first going to look at how can we do manipulations. How can we manipulate this? Okay, well, actually, first, let's take a look at this figure. So the function 1 over 1 minus x, that's you can see this red curve here, f, and it's like that. But then they give different s sub n's. So, they do partial sum with s equal to 2, 5, 8, 11. You can just see it's over as you increase n on the s sub n. So they're just plugging in. They're doing the sum formula, the power series sum formula with more and more terms, and it's converging. It's going to converge to f. But what you can see is that the way it's converging, it's like polynomial in each of these is like polynomial in character, right? You're getting as you increase n, you're getting a higher order polynomial is what you're doing. And that's why you can see when n is odd, it's like this. When n is even, it's something like this. Okay, so how can we manipulate this to create other function representations as power series? Well, okay, they say look at 1 over 1 plus x squared. So we can think about that 1 over 1 plus x squared is what? That's 1 over right? And so what is that? That's this. That's just this evaluated at minus x squared. So you come to the power series formula and just put minus x squared for x. You see? And then you take out the minus, that's minus 1 to the n, x to the 2n, so it's this alternating series. And then you do the normal series analysis. It's a geometric series, and it converges when the absolute value of minus x squared is less than 1, which means that's when x squared is less than 1. But you take the square root of both sides, and remember, if the square root of x squared is the absolute value of x, that's something, you really need to remember that. The absolute the square root of x squared is not x, it's the absolute value of x. And why is that? Because you minus 2 so these two, both of these are equal to 2. This is not equal to minus 2. So you have to take the absolute value. This can't be a negative. This can't be equal to a negative number in any situation. So, okay, so the interval of convergence is -1 to 1. And it says, of course, we could have determined the radius of convergence by applying the ratio test, but that much work is unnecessary here. Yeah, they don't have to test the endpoints because with a geometric series, you know that anything that makes the endpoints the common ratio greater than or equal to 1, the absolute value is not going to converge. So this is the interval of convergence. You could test a geometric series with the ratio test, and that would work. But if you can see it's a geometric series, you don't need to do that because we already know how to analyze a geometric series. Just take the absolute value of the common ratio needs to be less than 1. Okay. Find a power series representation for 1 over x plus 2. So again, we know what this is as a power series. The power series representation of this function. So how can we manipulate this? Like how is the form of this similar to this? Well, we've got this. So this is 1 over, let's do it like this, 2 plus x. Well, we've got the x here. You know, we could write this as 2 minus x. But it's this 2 here that's different. We need to make this into a 1. So we can factor out a 2 and we get, factor out a, factor out a 2 and then you get, okay, so now we're close. We can say this. We can say, so 1/2 times, and then we've got 1 minus x over 2. And there you go. We can say that this is equal to the, like we can just focus here because we can bring this constant factor outside the summation, the power series summation. And now we've got f of minus x over 2. So we plug minus x over 2 into x for this power series. You see, there's minus x over 2 to the end. Just bring out the 1/2. And so when you simplify it like this, this technically isn't a geometric series, but you could just treat this like a geometric series and analyze when is this the absolute value of this less than 1. So in this case, this is you could look at this as a geometric series. But this technically isn't because you have like they both technically aren't because it's like the common, you have a common ratio, but then it's not a constant term on each. So for each term, it's not the coefficient's not constant. So it's technically not a geometric series, but you can analyze it from here that way because as long as the absolute value of this is less than 1, then it's convergent. So they do that and they solve this absolute value inequality and get that this is the interval of convergence, and you don't have to analyze the endpoints because we know a geometric series isn't going to be like at -2 and 2, the common ratio is going to be greater than or equal to 1, or it's going to be equal to 1. So you know it's not convergent. Okay, here's another manipulation example. What about how can we represent x cubed over x plus 2 as a power series? Well, we just did 1 over x plus 2. So what we can think about is we can take this here, that's 1 over x plus 2, and just multiply by x cubed. And what's nice is that you have to remember that x cubed, or x, is not a function of n. So it's effectively like a constant with respect to the summation. The summation is going from n to infinity. The summation is all about n. The only reason you can't treat this the x to the n as a constant is because of that n. Because it's raised to the n, so it's tied to an n. But just x cubed, that's like a constant, so you can just move that around, or you just bring it in, and so you just bring the x cubed in. See, that's powerful, right? The fact that we can just bring the x cubed into the summation, that gives us a lot of versatility to create different function representations as power series. And so, yeah, you bring the x cubed into the summation and just do some algebra, and you can see that this is just another common ratio. You know, it's like geometric, but this technically isn't a geometric series. But don't worry about it. If you're not sure if it's like technically geometric, meaning that you know, if it's not technically geometric, then you can't just look at and say, is the common ratio the absolute value of that less than 1, then just do the ratio test, right? So they simplify this a little bit more. If you come here, so now it's starting at 3, and so now you can see it's just x to the n power, so it's a little, the a sub n is a little more recognizable. But yeah, this is technically not a geometric series, so just do the ratio test. That's what we're going to do. If we have a common ratio like this, but the constant, the coefficient on each term is not constant, so it's not a geometric series technically, we'll just do the ratio test. We'll determine the radius and the interval of convergence. Okay, now we're going to talk about the idea of differentiating and integrating a power series. And so why are we talking about this here? Well, the idea is, so our base power series function is 1 over 1 minus x. Well, what's the derivative of this? Okay, well, the derivative of the top is 0 times the bottom, then minus the derivative of the bottom times the top. So that's just going to be 1 all over the bottom squared. So it's 1 over 1 minus x squared. Well, if we can differentiate the corresponding power series representation of this, well, then now we have another way of, we can represent this function as a power series. Okay, and similarly, what's the integral of this? What's the integral of this? That's going to be minus natural log of the absolute value of x minus 1, but we know that if we wanted to, we could just write this without the absolute value, right? So now we're missing like the left side of this function when this expression could be negative, but still, I mean, that's fine if we're just thinking about that we're wanting to write a power series representation for this function, just a standard natural log without the absolute value. Because why? Because the derivative of this is equal to this. Okay, so if we wanted to find what the power series representation of this function is, natural log of x minus 1 minus natural log of x minus 1, if we could integrate the terms of this power series, then we could do that. Now, if you're still confused about, well, how could we take off the absolute value? Well, okay, once we get the power series representation, the domain is just going to be limited. That the domain of that power series is going to be limited in this case, because you can't have, this can't be 0 or negative. In this case, it wouldn't be limited. In the same way that natural log of x, this is limited. You can't have x be 0 or negative, but this is now x can be anything. Okay, so can we differentiate and integrate power series? The sum of a power series is a function like this, right? Here's the general, kind of a general form of a power series, whose domain is the interval of convergence of the series. We would like to be able to differentiate and integrate such functions. And the following theorem, which we won't prove, says that we can do so by differentiating or integrating each individual term in the series, just as we would for a polynomial, okay? This is called term-by-term differentiation and integration. So note that we're just talking about power series here, just talking about power series, because I think you might be thinking, well, no, we can't, there was a video a few videos ago on rearrangements in infinite series, and, it kind of would make you, to me, you might read that paragraph and think, well, how can we differentiate each term? How, well, no, that was only, there was only issues there when it came to conditionally convergent series. And we're just talking about power series, okay? So it's saying that there's a theorem we're not going to prove here that says that for a power series, we can differentiate a power series, and by what we're doing is effectively, you can think about it like you're integrating or differentiating each individual term in the infinite series. The infinite series, you can think about it that way. There's only issues with thinking about operating term by term or rearranging terms, etc., with those conditionally convergent series. All other series it's fine. Okay, so this is called term by term differentiation and integration. Okay, so here's the theorem, and it's really nice. If you have a power series, here's the general form that has a radius of convergence r is greater than 0, so that you need to have an actual non-trivial radius of convergence, either from negative infinity to infinity, or something that's not just, it's not just convergent at the center point, which means it's effectively not, it doesn't really converge, I would say. This is like a trivial case. So if it has a finite or a radius of convergence that's greater than 0, so this includes negative infinity to infinity, then the function f defined by, okay, there's the power series formula, is differentiable and therefore continuous on the interval. So on the interval, the entire interval except for the endpoints, it's differentiable and continuous. That's what the theorem says. That we're not proving here. And what is f prime of x? It's really easy. You come to this formula and do the power rule of differentiation. You just you bring down the n and then make this n minus 1. But maybe if you might have a power series that's defined with like the x minus a to the n minus 1, then you just bring down the n minus 1 and make this n minus 2. It's that simple. That's all you do. You could think about like what each term does, but just come to the formula and really we're going to see power series that they might have these complicated C sub n formulas. You go find the common ratio with the x term, right? The power series is going to have an x or an x minus a constant or x plus a constant, right? Go find that term. If you want to differentiate, then bring down whatever the exponent is exactly as it is and put it into the C sub n, and then just subtract 1 from the exponent, and you've differentiated it. Now, but that's not it. That's not it. There's one other thing to note, that with a power series, you're going to always have a constant first term, or I guess it's not a requirement, but yeah, so you have to inspect it. But typically with a power series, you plug in n is equal to the first term, and that's going to be a constant without the x in it. And so if that's the case, and most of the time it is, then you're going to need to, in the differentiated series, you're going to need to change the n from n is equal to 0 to 1, or just n is equal, you're going to have to just add 1 to the n. Maybe it starts at 1, then this would be n is equal to 2. Now, I think technically you could have a power series that doesn't, that the actual first term has an x in it. If that's the case, then you're not going to update the n, because that first term's not going to go away. I think it's the case. Yeah, you could have a power series and you could define it to where the first term doesn't. So like here, n is equal to 1, so the x minus a to the 0 power, you could have it where this starts at 2. Let's say this starts at 2. So where the first term actually is just has an x minus a in it. Well, in that case, you wouldn't, when you differentiate it, you wouldn't have to, this wouldn't go from n is equal to 2 to 3. It would stay at n is equal to 2. But you'd still differentiate the formula with the power rule. It's really easy. Go find that x minus a term to the whatever n type power term and do the power rule on it. That simple, that easy. Okay, and so again, they said this theorem that we didn't prove here. It's for any power series that has a radius of convergence that's greater than 0, that includes negative infinity to infinity, then it's differentiable and continuous on the radius of convergence, or the interval of convergence, not including the endpoints, and you could differentiate it this way. Okay, now you could also integrate the power series, and this is really simple as well. It's the power rule of integration, is how you're gonna integrate the a sub n with the power rule of integration. So you go find you find the common ratio, the x term with the common ratio, and do the power rule of integration. You add 1 to the exponent on the common ratio term, the variable term, and then divide that by that same exponent. This is x minus a to n plus 1 over n plus 1, and you're done. Now you don't ever have to update in this case, you don't ever have to change the starting point. And because actually with no terms with integration, no terms are going to go away no matter what, but you add a plus c though. Okay? Now we're going to talk about this plus c, how we deal with this plus c in a second. Okay, but that's how you differentiate and integrate power series. It says the radii of convergence of the power series in these two, they're both R. So yeah, so that's another thing to note. That's important. When you differentiate or integrate a power series, the radius of convergence doesn't change. The radius of convergence doesn't change. The interval of convergence might change. So what does that mean? Well, okay, if the radius of convergence doesn't change, it's always centered about the center point, right, for any power series. Well, the only thing is potentially after you differentiate or integrate, the endpoints, the endpoint conversion could be different. You have to recheck the endpoints. That's it. Radius of convergence is exactly the same. You just have to recheck the endpoints. It could be the case that changes. Okay, now note that you can think about these two processes, these differentiation and integration processes, as term-by-term integration or differentiation, right? You're differentiating a power series. It's the exact same concept as you're bringing the differentiation operator into the sum, and you're differentiating each term or integrating each term. That's how you're thinking about it. This is just for power series, but you can imagine but you could differentiate and integrate the vast majority of any series like this way. It's only going to be the conditionally convergent types that the issues are going to come up potentially with this term-by-term operation idea. Okay, we know that for finite sums, the derivative of a sum is the sum of the derivatives, and the integral of a sum is the sum of the integrals. Equations 3 and 4 assert the same is true for infinite sums, provided we are dealing with a power series. For other types of series of functions, the situation is not as simple. So, again, just everything we're learning here about differentiating and integrating an infinite series, we're just talking about power series. Just keep that in mind. Okay, note 2, although theorem 2 says that the radius of convergence remains the same when a power series is differentiated or integrated, this does not mean that the interval of convergence remains the same. It may happen that the original series converges at an endpoint, whereas the differentiated series diverges there. So you have to recheck the endpoints after you integrate or differentiate a power series. Okay, the idea of differentiating a power series term by term is the basis for a powerful method for solving differential equations. We will discuss this method in chapter 17. So yeah, it's important that we learn about infinite sequences in series. We're going to use infinite sequences in series, power series, etc. in differential equations, partial differential equations a lot, and just there's other applications. It's part of math and engineering, or any kind of problem solving with applied mathematics in any field. Okay, so in the previous section, we looked at the Bessel function. This was a power series with a complicating looking C sub n, but it's a power series, right? Just a common ratio to some, to the 2n power in this case, but a common ratio and a corresponding C sub n. It's not geometric because this C sub n is not constant for every n, but this is absolutely a power series. It's a common ratio with just a C sub n, multiplying it. C sub n coefficient, centered at 0. And we saw that the radius of convergence was negative infinity to infinity. So how do we differentiate this? If we want to take the derivative, it's really easy. I love this example to start. I love it because this looks so scary. Like, look at this. I mean, how are we going to differentiate this? Don't worry about all this junk, the C sub n junk. Go to the x term, the common ratio term. Here it's x, but even if it's x minus 5 to the 2n, it doesn't matter, and you're just differentiating that term. So you're gonna bring down the 2 sub n, and the 2 sub n is going to get mixed in with the C sub n, and then just subtract 1 from the 2n. So x to the 2n minus, if we come here, x to the 2n minus 1, And then that 2n got mixed in with the c sub n. There's the 2n. You can think about it like you're taking the derivative with respect to x of this entire a sub n. So if you're differentiating something with respect to a variable, then all the other variables you treat as constants, except for the variable you're differentiating with respect to. So the n's are constants. You don't think about differentiating those. It's just the x term. So you have like x to the 2n. Well, 2n is a constant. So that's the power rule. The power rule is only if you have like x to a constant. Like you can't have x to like the x and use you can't do that. Like dx of x to the x is not equal to x times x to the x minus 1. No. The power rule is strictly if you have an x or some variable, x or x minus a, some x variable to a constant. Well, in this case, the n is constant. Okay. So now they're saying, how can we express this as a power series? Well, we saw that the derivative of 1 over 1 minus x is 1 over 1 minus x squared. So we come back to our base function we were working with, this. So if we differentiate both sides, we get 1 over 1 minus x squared. Okay, so then we just differentiate this. Bring down the n, x to the n minus 1, done. So they change the n to n is equal to 1. Now what they do is they convert this back to starting at n is equal to 0 to get x to the n, so that's a good idea. And there it is. Really cool, right? They differentiated the base function, got this. Then they differentiated the power series. And they went from n is equal to 0 to n is equal to 1, but then they just switched it to starting at n is equal to 0 and just kind of manipulated the formula a little bit to start at n is equal to 0, the sum. And you could do it however you want. You could leave it like this if you want. And there you go. That's a power series representation of this function. Oh, and then here, yeah. So if we come back here, what is the radius of convergence of this? Like, where does this converge? Well, it's the same radius of convergence, minus infinity to infinity. Okay. Here, what about this? Well, it's going to have the exact same radius of convergence as this had, which was 1 centered at 0, but but you still need to check the endpoints though. I'm not sure why they don't recheck the endpoints, but the radius of convergence doesn't change, as well as the center point of that radius of convergence. And then you just have to check the endpoints. So I'm not sure, I guess because this is still, I'm not sure why they don't check the endpoints, but you would check the endpoints. Okay. Find a power series representation for the natural log of 1 plus x. So, okay, what is the derivative of the natural log of 1 plus x? That's okay. Now, this is, what is this? This is, we can write this as okay, well, we already worked this problem. Okay, so what we can do is we take f of x is equal to, it was, our base function was 1 over 1 minus x. We just put that as f of minus x, and we're going to get we put that in minus x into the power series formula, right? Then we integrate that. So, okay, here's 1 over 1. Why? Because, okay, this is equal to this, right? And so so what they do is, let's see, what do we have here? So if we come back, this was sum from n is equal to 0 to infinity of x to the n. That's what the original function was. Okay, so 1 over 1 minus x so this, then, this is f of x. But here we've got f of minus x, so we've got minus x to the n. So that's minus 1 to the n, x to the n. Okay? We want to integrate this power series because if we can find the integral of this power series, we're going to get another power series, right? Well, okay, but what's the other side of this equation? That's this. So when we integrate this, we get natural log of 1 plus x. So then we'll have the power series representation of natural log of 1 plus x. And so what is this integral? Well, you just come to, it's going to be this, but you do x to the n plus 1 over n plus 1. And you don't change the starting point, just add the plus c. So let's see, we've got, so n plus 1 minus 1 to the n, x to the n plus 1. There's the integral. So that's the power series representation of natural log of 1 plus x, right? Because we integrated the power series, and then we also integrated this and got this, but then they update it to where if you start at n is equal to 1, well, then plus c. Yeah, we got to add the plus c over here. Okay, but then they update it. If you start at n is equal to 1, it updates to this. Okay, now, as far as the radius of convergence and all that, you can, we'll work example problems on that, but you could just do the ratio test if you need. If you're confused, just do the ratio test and get the radius in interval of convergence. Okay, but what about the c, though? To determine the value of c, what we do is we put x is equal to the center point. And then with that, you can solve for c. In this case, c is equal to 0. So here's there it is, natural log of 1 plus x, and there it is. There's the power series representation. Okay. Can we find a power series representation for f of x is equal to the inverse tangent of x? Well, what you do is you just think about what is like the derivative of this, or what is the integral of this? Is the derivative or the integral of this result in a form that, like a base form or something close to a base form? So, yeah, the derivative of this is 1 over 1 plus x squared. Is that our base form, the 1 over 1 minus x? No, but it's close to it. In a previous example, we actually found this power series from the base form. So we can use that. If we take the integral of this, as well as the integral of the power series of this, we'll get the power series of this. And so that's what they do. And then they put the x is equal to the center point to get the constant, and there you go. Inverse tangent of x is equal to this as a power series. And they're comparing we know the radius of convergence of this was 1, therefore the radius of convergence for the inverse tangent series is also 1. We have to check the endpoints. Okay, let's take a look at this last example. So first, it wants us to find the integral, this integral as a power series. So we see 1 over 1 plus x to the 7th. We can use the manipulation of our base series with, so you write this as f of minus x to the 7th. That's right. So you can create a power series from the manipulation of the base function, then integrate it. Okay, and so that's what they do here. There's the integral. Okay, so now part B, how can we think about this definite integral from the perspective of the power series? Well, what you can do is, when it comes to a definite integral, the c doesn't matter. So we'll just say c is equal to 0, right? You can ignore the c effectively. So Now, after you integrate, every single term has an x in it. So the portion that you're evaluating with x is equal to 0, everything goes to 0. So it's really just this. All we're doing is we're thinking about this here with no c, but you're plugging in 1/2. Okay, so they plug in 1/2, and here's the corresponding. What you get is a new series, where the a sub n of the series is this, and it's an alternating series. Now, if we come back to the question, it says we want to approximate this correct to within 10 to the minus 7th. Because the idea is, like in reality, we can integrate this. We would just go ahead and integrate it like normal. But we're trying to get the feel for, if we have a function that we can't integrate, we could think about it as a power series and do estimates. So if we were going to estimate this definite integral, then to correct to within 10 to the minus 7, then what we're doing is we're thinking about what is this series here. Can we get an estimate for the sum of this series? Because this is the definite integral. The series with this as the a sub n. Can we get an estimate for what this is equal to, correct to within 10 to the minus 7th? Well, yeah, we can apply the alternating series test here to show that it's convergent based on the alternating series test, and then use the alternating series test R sub n estimation method. And that's what they do. And so they showed that if you plug in n is equal to 4, if you sum the first 4 terms of this, that's going to be correct to within 10 to the minus 7. So there's the estimation for the definite integral. Okay, so now let's work some example problems, and we'll go through, if you feel like you missed some of the details, we're going to work a bunch of examples and go through every detail here, including I think I didn't spend much time talking about the different radiuses of convergence and the intervals of convergence. And so we're going to go through all that in detail in the example problems.